Hey guys, happy Thursday. Almost through the week. Hopefully you guys saw the news here that next week we'll have school just normally, just like how we have been. And then the week after that, you guys have nothing that week. So you get like a second Christmas break before we start the second semester. Some of you might be transitioning to online permanently. Some of you are coming back into the classroom, so I know it's kind of just crazy stuff going on. But if you guys have any questions about any of that stuff, just send me an email, send me a remind, and I'll make sure to hit you guys up and make sure that you know what's going on. Okay. We've been talking about exponent rules. Yesterday you had that practice worksheet, with just all the rules we talked about so far. There's a couple more things with exponents that we need to talk about and problems that we need to know how to do. So first off, there's this really interesting thing with fractional exponents. So we haven't seen these yet, but you could have, for example, 6 to the 1/2 power. Let's say something like that. If your exponent's a fraction, you actually know what this looks like, which is really surprising. But fractional exponents are actually where we get square and cube and all sorts of roots from. All right? If something is to the 1/2 power, that's actually the square root of that number. And it's really interesting how this works with the fraction as the exponent. So let's say I had x to the 6/11th power or something like that. All right. The way that this works is this top number, the numerator, stays with the base. The denominator goes on the outside, and that's what kind of root it is. So this could simplify into x to the 6th, and then we have a root, and what kind of root? It would be the 11th root, because that's the denominator. That's where we get that from. So if you check this out up here, the 1 is still on the 6, right? We just don't write that 1. If it doesn't have an exponent, it's really 1, right? The 2 is out here. Sorry, choking. So if you see a root without a number on the outside, it's always a square root. So it's always a 2. Which is weird because in math, usually when we don't see something, it's a 1, right? So if you don't see anything out here, there's always a 2 there. So I can put things in roots or out of roots however I want. Let's say you had something like 16 to the 3/4 power, right? And you want to write that as a root. You keep the numerator on it. You make your root. You take the denominator. That's what kind of root it is. So if I actually wanted to figure out what this thing was, you could, in your calculator should be able to do this. You could just do 16 to the 3/4 and it will tell you. Or if you did 16 cubed, got that answer, and then took the 4th root of that number, you could also do that, and they would be the same number, which is pretty cool. Likewise, if you wanted to take it out of a root, so if I had the 5th root of 2 squared, I could take it back out and write it in exponent form. The 2 would be the top. The root number is always the denominator. So the 5th root of 2 squared is the same thing as saying 2 to the 2/5. Okay? So that's one thing that you need to know. And that's pretty crazy that you probably never knew that. But I don't know how much of this you guys did last year. But in my class, my pre-algebra class, this is one of the first things we do in the year. And we talk about how square roots undo exponents. Right? So for example, if I had something like x squared equals 16, to get rid of the squared, we need to take the square root. They're inverse operations. and I could square root that, and I could get plus or minus 4, right? Positive and negative 4. This is kind of why they're inverse operations. I don't go into this depth with my pre-algebra kids and show them like how fractional exponents are actually what square roots are, but it kind of makes more sense now that you know that they're inverse operations of each other. So yeah, pretty cool stuff. All right, so there's that. The other type of problem I want to talk about with you guys today is one that looks like, let's say you had something like 3 to the x minus 17 equals 3 to the 3x plus 29. Okay? On these problems, basically what we're looking at here and testing you on, I guess, is that if the bases are the same and they're equal to each other, that means that their exponents would also have to be equivalent. So the bases are both 3. That means their exponents both have to be the same thing. So what would x have to be in order to make those exponents the same thing? Well, as soon as you get these bases to be the same, what we're going to do is we're just going to drop the bases completely and set this equation up with just the exponents. Like that. So literally, because they're both a 3, we can just get rid of that line, use the exponents, set those equal to each other, and then we can just solve for x. Minus 1x for both sides, you get negative 17 equals 2x plus 29. Minus 29, that's 30, 40, negative 46 equals 2x, and then divide by 2, and we get that x would have to be negative 23. So if x was negative 23, those two would be exactly equal to each other. Now that seems pretty easy, I'm hoping that seems pretty easy, but it does get a little bit trickier than that. Let me show you what I'm talking about. So sometimes, I'm going to steal one from the book, I think. Sometimes the bases are not the same right away. So for example, we have 27 x minus 4 to the x minus 4 equals 3 to the 2x minus 6. So, this is a little bit weirder because just these two things aren't the same, so that doesn't mean that those two things would have to be the same, right? The bases aren't the same, so their exponents don't have to be the same. So what we need to do is we need to change the bases so they're the same thing. How do we do that? Good question. So I always think of it this way. You take the higher number and you work down. So I want to turn 27 into a 3. Well, to do that, we need to think of it as 3 to some power. We need to use an exponent. So what I'm going to do here is going to do something like 3, and then I got to figure out, this is going to stay the same. What could 3 be 2 to be 27? Well, 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27. So I could rewrite 27 as 3 to the third. And then I know it would be x minus 4, like that. So here's what we did. We took 27. We rewrote it as the other number's base to some power. They have to be the same. Because now what we can do is we can do power to a power here, right? And we're going to distribute, right? I mean, you can think of it, distribute either way. Distribute the 3, that makes more sense. Distribute the 3 through, and that's going to be 3x minus 12 equals 3 to the 2x minus 6. So I did 3 times x, 3 times negative 4. That's where I got that from. And now I can drop the bases because they're the same. and just set my exponents equal to each other. And I know that's tricky, especially figuring out like, hey, what am I supposed to turn that into, Odie, right? Like, how do I know which one it's going to turn into? You don't always. Typically, when you start out, it's going to just turn into the other one. Sometimes you have to change both of them, and that's not fun. But you just think of what factors would these have in common that I can actually write them with an exponent. And then hopefully you can come up with a base that's pretty low that you can rewrite it as the exponent and then distribute your exponents like so. And then the rest of this, I think you guys will be fine with this part of it at least. Right? That's just x minus 12 equals negative 6. Add 12 to both sides, and you get x equals 6. So if x was 6, these two would be equivalent to each other. I want to do one more of those because I want to do one that's a fraction to kind of show you the difference there. All right. And then we finally have book homework and not a worksheet. I don't know if you like that better or worse, but either way. All right, so let's go with, that's not the one I want. There we go. 1 over 125 to the negative x over 2. And that's so small, equals 1 over 25 to the negative x over 3 minus 2. Let me make sure those are, I mean, I could do it either way. I'm trying to do this one that's in your book right here. All right, looks good to me. So, kind of weird, we have fractions. Well, what we need to do when we have fractions is remember our rules. How did it become a fraction? Probably because it was a negative exponent, right? Because with negative exponents, we talked about yesterday how you gotta flip them and turn them into a fraction. So what I wanna think about is, first of all, is there any way to write 125 as 25 times something? Definitely not, because 25 squared is way more than 125. So this is one I'm thinking about, maybe I can change both of these. Do they have some factor that I could rewrite them as? Well, the 5s kind of give it away on this one, I think, because I know I can write those as factors of 5. So this would be 5 squared, because 5 times 5 is 25, but it's on the bottom of a fraction, so it'd be to the negative second to get it out of the fraction. Does that make sense? I'm going to change it from a fraction, so I need a negative exponent, and then obviously 5 times 5 is where I get the 25 from. So there's that, and that's all going to be to negative x over 3 minus 2. On this side, I can rewrite it as 5. 5 to the third power is 125. But again, it's a fraction, so it's going to be 5 to the negative third power. And then I still have that outside, negative x over 2. So like that one, for example, that's tough. I know that's tough. So, you know, it's good for you guys to see this and kind of start using your brains a little bit, thinking that way. So now that we have the bases the same, what I want to do is distribute to get power to a power here. So negative 3 times negative x over 2 is going to be 5 to the 3x over 2. The negatives would cancel out. And remember, it's a fraction, you just go straight across, right? So 3 over 1. Over here, negative 2 times negative x over 3 would be 2x over 3. And negative 2 times negative 2 would be plus 4. So now I finally got my bases to be the same, and now they have exponents, so now I can just set the exponents the same. 5, oh, I don't need the 5. 2x over 3 plus 4. All right, cool. And then we can just subtract 2/3 x from both sides. Remember, if we're subtracting here, we need common denominators. So 3 over 2 minus 2 over 3. Obviously, you could just do it in your calculator, but you know, I usually don't. So I'm going to change them both to 6's probably. So that'd be 9/6 minus 4/6, which is going to give me 5/6. And let me move this down so you can see the bottom here. If I am going to get rid of 5/6, I'm just going to multiply by the reciprocal. 6 over 5 times 6 over 5. And go straight across. That would be 24 fifths. So, set it up. I got x equals 24 fifths. That's a lot of work problem. But it's a really good problem. And, you know, that is definitely rules that I do not teach my pre-algebra kids. That's definitely Algebra I level. So, cool. Try those out. Let me know if you have any questions. I gave you something from the book tonight. We're caught up with the book. We reviewed a little bit, and I think we're okay. So, yeah, jump on in. Good luck. We'll see you later.